Okay, so now let's take a look at independence. The formulas you've got here relate to those last two things. Here's the last one that we just did. Mutually exclusive, the intersection is empty, probability 0. If they're independent, then this is the one that governs it. The probability of landing in the intersection is equal to the product of the probabilities. That's the definition of independence. All right. That there. Here we go. Now, here is a set of outcomes for dice. And so we're going to look at these. We had one last time that was talking about mutually exclusive events, prime and even. And it turned out this one outcome was both prime and even. So that was not mutually exclusive. So now what we're going to see is that they're actually dependent. And if they're not mutually exclusive, that doesn't mean they're dependent. Or if they're mutually exclusive, it means they are dependent. If they're not mutually exclusive, they might be independent or not. So now we look at their probabilities. So if we look at the probability of A, that was the probability of rolling a prime number. Now if you look back at the outcomes we did before, the probability of rolling a prime number turns out to be there are 13 ways to do it. So it's 13 out of 36 is the probability of rolling a prime number. All right, then if we also counted up all the probabilities of rolling an even number. So for an even number, it turns out half of them are even. So there's 18 out of 36 were even. Okay, so those are our two probabilities. Now, what's the probability of rolling an even prime number? That turned out to be 1 out of 36. There's only one roll out of 36 that's both even and prime. But now if you compare, if we multiply these two together, we get 13 over 36 times 18 over 36. That does not equal 1 over 36. Because 18 times 13 is, more than 36. It doesn't cancel out. So, these are not independent. Okay? That shows us that they're not mutually exclusive and they're not independent. Let's look at some more die rolls, though, that on this grid here, I've listed all 36 of them, and I want to talk about that a little bit. We'll look at some examples that are independent. Okay. Now, on this grid, I've got red outcomes across here, like there's one die that's colored red and another one that's colored green to make it clearer about the difference between, say, a 2-1 and a 1-2. In a 2-1, it's the green die that's a 2 and the red die is a 1. In this one, the green die is a 1 and the red die is a 2. So we're distinguishing between the two on this one. Now let's look at another event now. Let's look at the probability that the red die has a 6, a total of 6. Okay, so let me make sure I've got some working space there at the left a little bit here. All right, so let's let A be that the red die is equals 6, okay? Let me write that a little clearer. The event here that the red die shows 6. Okay? Doesn't say what the other one is, what the green die has on it. So let's look at the event here. If the red die is a 6, that's this column out here. So this set of outcomes here, that's set A, okay? So far, that's what one event is. Okay, let's look at another event. Let's look at now another event where you roll an even number. Okay, so let's let B be the event, an even number. Okay. Well, what number is even? Well, the total, is even, okay? So in fact, half of them are even. We've already seen these in the previous problem, but let's spell them out. Which ones are even? Well, anything that's odd is going to be on this column, or this diagonal here. So this is even. No, that's not a very good marker. Let's go with the black one. This one's even, 1 and 1. These are all even. Okay. These are all even. Okay, all the totals they give us 6. So that's 2, 4, 6. Here's the 8 totals. Okay, then there's the 10 totals. And intersect there a bit, right? And then there's the 12 total around here. Okay, so right away, now we see that there is some intersection. Right? If there's no intersection, then they're mutually exclusive, and that makes them dependent. So in the first step, when we're looking at outcomes, if you see no intersection at all, then you know they're dependent. And the answer would be no to the question, are they independent or not? Okay, so now we've got some intersection. We don't know whether they're independent or not. What we're going to look at now is look at what's the probability of both happening and compare that to the probability of each happening and see if their product is equal to the intersection probability. Okay, so now, let's see. What's the probability of A? Well, there's 6 outcomes, so that's 6 out of 36, or 1/6. What's the probability of B? Well, there's 18 of them if you count them up out of 36, so that probability is 1/2. Half the outcomes are even. Okay, what's the probability of both happening? What's the probability of A intersect B? That's an even number with the red die showing up 6. Oh, and I left one off here. You see how it goes up here and stops? That one should have continued. The total of 8 is up here as well. There. Now we include that one as well. Okay, so what's the probability of both happening? Well, that's the intersection. That's this one, and this one. The intersecting outcomes. There's 3 of them. So that's 3 out of 36. So that's 1/12 if I reduce it. Now you can see why I'm advising you to reduce it. Now let's look at the probability of A times the probability of B. Probability of A times the probability of B. Well, that's 1/6 times 1/2, and that does equal 1/12. So these are the same, therefore they are independent. Okay. Just because they overlap doesn't mean this will always happen. But if it doesn't overlap at all, we know it won't happen. Okay, because then the intersection probability will be 0. All right, so that's an example of 2 events, rolling an even number and then rolling a red die equals 6, or one of the dies that you happen to mark 6. Those are independent. Let's look at some other examples of independent events in the next video.